Oh yeah, she would kill me.
Okay, hello everyone. Do you guys have any questions about the homework? Please feel free to put them on the chat in case you have any questions. I'll look at them, but before we do that, I definitely have to comment on the quiz. Okay, just to make sure you all got the mistakes. So I usually only comment on the problem that you had difficulties with. So the first one, the second one, it was discussion of the solution. So I gave you a simple system. And my first question was find the echelon form of the augmented matrix. So we put the augmented matrix in here and find the echelon form. So that was not a hard question. So I have to make this into a 0 minus 2R1 plus R2. And we got here 1, 2, 1 minus 2 plus 2 is a 0. And this is going to give me a squared minus 4. And this is a minus 2. So I told you to stop at the echelon form. I did not want you to go any further than that. Okay, now my second question was the following, and that's where the difficulty came. The second question is, for which values of A, value of A solution is unique. It means I have one solution. Okay, and the answer is actually simple. We have one solution if every variable, so here we have a system with two variables. So this is basically X and Y. So we have solution is unique if both variables are basics, okay, if we have no free variable. But how can this occur? How can this occur? Free variable occur if each column that corresponds to each one of them is a leading. The column that corresponds to the X variable is a leading. The column that corresponds to Y, then we may not have a leading here. To ensure that we have a unique solution, we need a leading entry right there. What does it mean? It means no free variable. And this will occur when a square minus 4 different from 0, period. It does not have to be equal to a minus 2, which is a lot of you wrote. There's nothing to do with that. What I want is that this term here to be a non-zero term. It means a should be different than plus or minus 2. And that will definitely guarantee the uniqueness of my solution. Because once this is not 0, then I have a simple system. So once this is not 0, let us say I have 1, 2, 0, and I don't care what I have here. This is really irrelevant. I can have like pi here. It's really irrelevant. As long as this is not 0, so let us say this is a 5 in here, I don't care. As long as it's not 0, as long as this is 5, then I can solve. I will have y to be pi over 5 because now I can solve. Why I can solve? Because this can be read 5y equal to pi, giving me y equal pi over 5. So I don't care what's in here. The only thing I care about, I want this to be a non-zero term. And that will guarantee a unique solution. So I can solve for y. Now the first one will allow me immediately to solve for x because it's 1 minus 2y. Y has a unique value, x will have a unique value. Okay, so that's actually what we need, no more, no less. Some of you put those equal to each other. No, I don't want those to be equal. This is 5, this is pi. They don't have to be equal. The only thing I want is I want to guarantee this is not a 0. All right, so that was the one of the problem on the quiz. And you guys, as I told you day 1, I'll tell you day 2, I will tell you for the rest of the semester. This course is language based. If you don't understand the language, you will be lost. So please study, please read the notes, study the book, go over the lecture and do your homework. That's the only way you're gonna move forward. All right, the other question that you guys had difficulties was the last one. My question was, okay, how can you visualize the span of 2, 2? So let us remember, the span is all linear combination. If I have one vector, what do I mean by linear combination of one vector? That's the only hard scenario. Linear combination of one vector, it means all the scalar multiple. It means all vectors, all of them of the form C times 2, 2, where C is a scalar. Okay, that's what's the span. Every vector that have this form. So if geometrically, you know, I have the vector 2, 2, this is my vector 2, 2. And if I start taking every possible scalar multiple, but if you take scalar multiple of this vector, you stretch it either this way or you stretch it that way. So there is no way you can get everything in R2. You get only things on this line. So you're basically stretching it in both ways. That's what you are doing. So in this case, the span is just a line through the origin because 0 is in the span. It corresponds to C equal to 0. And a nice way to describe it is the line in the direction. What do I mean by in the direction of the vector 2, 2? Now, of course, I did not expect you to write this. I just wanted you to know that it's a line. So but now it's nice to start writing it as a line through the origin in the direction of 2, 2. It means this is a line, start from here, and it moves in this one direction, which is 2, 2. There is no other direction for that. Okay, so a lot of you messed up this question, and honestly, I really don't know why, but whatever. Now, the second one was, I gave you still 2 vectors, 8, 2, and 2, 3. And my question was, okay, what's the span of those? It means if you take every possible linear combination, it means all C1, if I call this U, and then I call V, everything of the form C1U, C2V, where C1, C2 are scalars. What do you get? And this is the picture that we try to draw a lot on the board. So I gave it to you. 8, 2 is a vector like somewhere in here. That's one vector. And 2, 3 is a vector somewhere in here, for example. And the idea was if I take every possible linear combination of those two vectors are not scalar multiple. As we said several times, you can get everything in R2. It means if I give me any vector, it means if you give me any 2 ordered pair, I can reach by following those 2. So the span of those is actually all of R2, meaning everything in R2 can be written as their linear combination. And finally, I gave the following vector, and then we have to proceed. So my final question was the span of the following. It means every possible linear combination of those. It was 639, and 2, 1, 3. So that's my vector u if you want, and that's my vector v. And this will put me in R3. It means in the 3 plane because I have 3 coordinates. And what's the span? Usually we said it is a plane, but here if we realize that as long as those vectors are not scalar multiple, but here if we realize from 6 to 2, you're multiplying by a third. From here to here, you multiply by a third. From here to here, you multiply by a third. So what does tell me geometrically? If this is my vector u, that's my u, my v is a third of it. This is my vector v. So when I'm going to start taking all linear combination of those, I am still along this line. I cannot really leave it. C1u will stretch, but you're adding a vector on the same line. So this is going to be a line because they are scalar multiple. So v is a third of u. So it's a line. That's how we visualize it through the origin and in the direction. In the direction, what's the direction of this line? Because you have a line, it's characterized by the direction of the line. It means in how it moves. In the direction of either u or v, I don't really care which one you pick because u and v have the same direction. All right, so those problems gave you trouble. Please make sure you grasp those ideas, all right? So I'm expecting questions and I don't find any questions. Do the homework, do the homework. Okay. How do we do number 33 on 1.4? Okay, I'll look at that and then I will go back to do that. 33 on number 1.4. So I'll put the problem in front of us. Okay, that's section 1.4. All right, 33. I'll read it because it may not be very clear. Suppose A is a 4x3 matrix, all right? So already you have to have a picture in your mind. So 4x3, this one, it means we have 4 rows and, okay, 4x3. And B is a vector in R4 with the property that AX equal to B has a unique solution. So you're solving AX equal to B, you solve it, and you get a unique solution. So you're solving the system and you get a unique solution. So the system is consistent.
We can't see the paper.
What? Yeah, I will come back to it.
Oh, okay, sorry.
Right there. Is it better? Yeah. So it's 4x3. And B is a vector with this property. What can you say about the reduced echelon form of A? So let us analyze the picture. Solving AX equal to B, which I will remind you, it means solving the system with augmented matrix AB. Okay? So when I solve the system with augmented matrix AB, I'm going to have a unique solution. So what should be the picture in here for this to happen? So what should be the reduced echelon form of AB first, and then we worry about A. So I have a solution. It means when I solve the system, I put in an augmented matrix. The result is unique solution and consistency. What's going to be the scenario in there? How many leading I'm going to have? Question addressed to you. All column will have leading. Very good. All column have a leading. Means I should have a leading here because it's a unique. I should have a leading here because the solution is unique and they want the reduced echelon form. I need a leading here because the solution is unique. Also, I have consistent. So this could be anything, this could be anything, this could be anything, and this has to be 0. Okay, so that's how you analyze this problem. So AX equal to B has a unique. It means when you try to solve it, which really boils down to take the augmented matrix AB. So when you reduce it, the reduction should show you a unique solution. So to have a unique solution, it means there is no free. Every column should have a leading, of course, except the last one, because we have a solution. So that's the scenario we have. All right, Chris? It makes sense. Okay, very good. Now I will, for 5 minutes, we will basically recap what we did last time. So I'll make sure that you guys totally understand it, because it was terminology more than concepts, I would say. More terminology than concepts. So let us recap a little bit what we did, and then we move on. So the idea is we have a matrix A. This is my matrix. I'm just making up a scenario. And we have a vector B. So let us remember. We defined A times B in 2 different ways. Who can remind me the first way? Who can remind me the second way? Very quickly, please. So we defined it in 2 equivalent ways. It means they give me the same answer, but it's a point of view that will change.
Linear combination.
What was the first definition of A times X?
The definition is a matrix, product of a matrix and a vector, correct?
That's the second one.
Oh, okay.
That's what we call the row column. Okay.
Linear combination.
Linear combination, exactly. The first one is as a linear combination of the columns of A. So what's a linear combination? It means, and those are the weight. They both give me the same answer, that's for sure, but a different point of view of looking at it. So the first one is x1 times the vector 1, 2, 3. The second plus x2, these are the weight 4, 5, 6. The row column is the row column. It's like a dot product. It's x1 plus 4x2. And then it's 2x1 plus 5x2. And finally, 3x1 plus 6x2. Now, of course, if you add those vectors, you're going to get that. But this is like a point of view, which is definitely crucial to see it. Okay? Now, question number 2, fairly simple. This is your matrix A, and it's your vector X. And this is your vector B. What does it mean to solve AX equal to B? It means which system we are solving. And what's the augmented matrix? The system we are solving is, if we use this definition, it makes it very easy. It means I'm solving the system, x1 plus 4x2 equal minus 2. So solving that, it means solving the system. Once we understand the language, things will be easy for us. Equal to 0. Okay, and it means the augmented matrix, as I said, is A, the coefficient, and B, that's my vectors. Right? Now, again, questions to remind you. Suppose it's the same A, and I tell you the following. -2 minus 1 is a solution of that. Means if I put the -2 here, -1 here, I multiply, I get -2 minus 1. So suppose I tell you that. Now my question, write, this might be, write B as a linear combination of the columns of A. Okay, so let us solve, you solve, whatever, you took the system, you solve it, you find that this vector is a solution. Now I'm gonna ask you to write B as a linear combination of the column of A. Is it an easy or a hard question? Easy or hard? Let us understand it. What does it mean this is a solution? It means when I take the matrix and I multiply it using row column, using anything you want, I should get that. That's what it means, a solution. 5, 6. Is it -2, -1? That could be -1, sorry. -2, -2, -5, and so I thought plus, sorry, it's +2. Very good. So this is 2 minus 4, that's 4 minus 5, and that's 6 minus 6, correct. So if I tell you this is a solution, now I'm asking you to write that as a linear combination. Is this an easy or a hard question? Quickly. How can I use that info to write this vector as a linear combination of those? One, two, three, 4, 5, 6. What are the weights? Remember this interplay in the definition. This interplay of definition. If this time that give me this, it means that if I use the linear combination definition, it means 2 times the vector 1, 2, 3 plus, right, 2 minus 1 will give me that. Okay, that's where the interplay in the definition is. It means that the weight that will let me write this vector as a combination of the column of A are nothing more than the entries of this vector. So two definition, but definitely the interplay is very interesting between them. All right. The last question, unless you guys have any problem, is the following. Again, we make sure understand the terminology. Suppose I have this system and I ask you to give me a matrix and a vector. So that solving this system is really equivalent to solve the matrix equation. I mean, solving the system is really equivalent to find a vector. When I multiply it by this, I get the vector B. What should be A? What should be X? What should be B? Because every system, we're going to rewrite it this format. It means solving it, really solve finding this vector here. So what should be A? What should be the vector X, the one that I'm going to be looking after? And what should be the vector B? The vector A, matrix A, is nothing more than the coefficient matrix of the system. The vector X is the vector whose entries are the unknown, and I have 3 of them. The vector B is the vector of the constant term. 2 times 3. Okay, so that's 3. So every system, since now on, okay, we rewrite it sometimes in this format. And every time I write X equal to B, I really mean the system. Okay, so this is a recap for all the terminology we did last time. I get back to you. Do you guys have any questions about the homework? Please do the homework. There is no way out of that. Okay, so before I start section 1.5, any questions?
Yes, please. Could you please bring back the last sheet for a moment, please?
This one?
Yes.
Okay.
Okay, so let me just down real quick.
Today we're going to start section 1.5, and 1.5 is since we solved the system in section 1.1, 1.2. And the way we wrote the system, the solution is we said, okay, x1 is blah, 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 x2 is free, x3 is blah, 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 x4 is free. We did something along those lines. Now, because we're writing a system using this notation, I'm going to start writing solution only as vectors. So I want to write as vectors. So the question is, if I have infinitely many solutions, how can I write solution as vectors in a correct way? And what's the best writing that will help me to understand the solution a little bit geometrically? So the goal of this section is to whatever we did before, rewrite it using vector notation and try a little bit to understand the solution geometrically as as much as we can. Okay, can I remove the paper now?
Go ahead, please. Thank you.
Now, so section 1.5, solution set of a linear system. Okay, now we're going to describe all possible solutions. First, a definition, simple definition. A system of linear equation is called homogeneous if it can be written in the form ax equal to 0. It means the constant terms are 0. So we call it homogeneous if the constant terms are all 0. So for example, if I take this system, I can write it in the following format. Okay, this is the 1, 1 minus 3, 2, 1 minus 4, 3, 2 minus 7, times x1, x2, x3. You realize I'm always writing the same thing. If I use the row column, that's really what I have, equal. That's an equation, the 0 vector. It means 0, 0, 0, or sometimes we write 0 vector like this. So this is my system that's homogeneous, means all those terms are 0. Now one single simple comment about homogeneous system. Homogeneous systems are always consistent. It means they always have a solution. Why? You can give me one solution of a homogeneous system. So that's a system. All those terms are 0. I'm telling you that there's always a solution. Who can give me one solution? 0, 0, 0. Absolutely. If I put in 0 here, 0 here, 0 here, 0, 0, 0. So because x1 equal x2 equal x3 equal to 0 is a solution. It's always consistent. Or I can say the vector x equals 0 is a solution. Okay, so you can say either one. So it's homogeneous, they always have a solution, which is x1. Sometimes this solution, the 0 solution, is given a name and called the trivial solution. So this is called the trivial solution. And a word that will be used, trivial solution, means the solution that consists of zeros only. Okay, so homogeneous system already, they have one advantage. We don't have inconsistency in them because there is always a solution. But we know a solution is infinite, and now we have to learn how to write a solution when it is infinite using vector notation. Solution set of a system is nothing mean that all the solution of a system. So the book used the word solution set. Since a system have infinitely many, can have infinitely many, solution set is basically they mean all of them. So now I'm going to take this problem and we're going to solve it. So now my question is, solve the following problem. The new thing I'm going to do today is we're going to write the solution in what we are going to call parametric vector form. So we're going to solve it exactly the same way we always do, but there is a little bit, add something to it. I'm going to write it in parametric vector form. And that's really the new part. So, but solving is solving. Solving, there is nothing new in it. So we take the augmented. So I'm going to solve it. I know I have one, but we may have more. Okay, so this is equivalent to. So we're going to do it. Right, so 1, 1 minus 3. I'm going to make this into a 0. So minus 2 plus 2, that's a 0. Minus 2, that's a minus 1. Minus 2, that's give me a 6. Minus 4, it's a 2. That's a 0. That's a 0. Minus 3 plus 3. Minus 3 plus 2, that's a minus 1. And that's minus minus. That's going to give me a 9, which is going to give me a 2. And this is a 0. So I have a leading. I have a leading. Everything below it has to be a 0. Now, obviously, you see what's really happening in here. So I'm going to have a 1, a 1, minus 3, 0. So far I am not doing anything that we haven't done several times. I'm going to a little bit switch the sign, and actually let me do it slower. And then I'm going to add. By adding, I will have minus 1, this is 0, minus 2 plus 2, it is 0. Okay, and finally, I will go to the reduced echelon form because it's very simple problem and I solve. So 0, 0, 0, so I have a leading in here, I have a leading. And then 0, I'm gonna cheat a little bit. I skipped a step. And then I will have 1, minus 1 plus 1, it's a 0, minus 1 is 0. So far, nothing new. I'm working with echelon form. And now let us solve the way we used to, and then what's new. So I have leading here. So I have x3 is free, and x1, x2 is basic. And the system that corresponds to my augmented matrix is x1 minus x3 equal to 0, x2 minus 2x3 equal to 0. So the general solution so far is the following. The general solution is always we're going to write it x1, x2, x3. I don't write only x1 and x2. This is wrong because the solution consists of 3 numbers. So if you only write x1, x2, what is x3? So we have to write them all. So x3 is free, x2 is 2x3, and x1 equal x3. So far, everything should be understood, and you guys did fine on that problem on your quiz. And now the new things. I'm going to introduce 2 things. First, the free variable, it's kind of confusing to keep it x3. I'm going to introduce a parameter. So I'm going to set x3, which is the free variable, to be equal to a parameter t, where t can be any number. The book avoids this, but I think it's clearer for the student if we let x3, we give it a name beside x3. So we're going to call it t, where t is any number. And we're going to first rewrite the solution in terms of t. So rewrite in terms of t. So far, I'm just adding, I'm going to add 2 things. So this will give me x1 is t, x2 is 2t, x3 equal to t, where t can be any number. So I have infinitely many solutions. Every time I change the value of t, I create a different solution of the system. Of course, 0, t equal to 0 will give me the trivial solution, and then later on. Now, parametric, the idea of parametric, it means introducing this parameter t. Now, what's the vector form? Now let us rewrite this in vector form. It means I'm gonna write the solution as a vector. And the reason we write it as a vector because we wrote the system in the form a times x equal to 0. So, and this is a vector. So now we're gonna write the solution also as a vector. So how do we write as a vector? Okay, so let's do that. I will push this up so you guys can be with me. Okay, you write it like this. So now vector form. Okay, we say the solution. So suppose vector x is a solution. It means the entries satisfy the equation. So x has 4 entries, 3 entries. x1, x2, and x3. So step number 1, what's the form of this vector? x1 is t. x2 is 2t. x3 equal to t. Okay. The last step is we're going, since it's a t and a t and a t, we're going to factor out the t. And that will be important. If I factor out the t, I get 1, 2, 1. So that's way, this way of representing the solution is called parametric vector representation. Introducing T, that's the idea of parametric, rewriting it as a vector called parametric vector representation of the solution. What is the benefit of this way of writing it? First, it's more compact, that's for sure. But there are more benefits to that. Are you with me so far? Okay. So what does this really tell me? So this is a system, basically. That's the system I am solving. And this tells me that every solution of the system has to form a scalar times 1 to 1. So geometrically, so that's the solution, you're done. But now geometrically, can we visualize the solution? So geometrically. How can we visualize the solution? Every number that satisfies this equation, the x1, x2, x3, will have the form t times 1 to 1, where t is any number. So how can I visualize the solution in this case? Can I actually visualize it? Every solution has 3 components. So every solution is a point in R3. But what characterizes a solution? Every solution is a scalar times the vector 1 to 1. It means if I draw the vector 1 to 1, 1, 2, 1. This is the vector 1 to 1. Every solution is nothing more than a scalar times this vector. So every solution can be visualized as a point on this line. And this makes sense for those who are seeing 261, which is most of you already have seen it or are in the process of doing it. These are 3 planes in R3. And we're looking at their intersection. Now what is telling me that the intersection of those 3 planes is actually this line right there. So geometrically, the solution are all points, x1, x2, x3, all those points that are on the following line, that are on the line, very specific, that go through the origin, because t equal to 0 is giving me the origin, that go through the origin. And a nice way to define it, and in the direction of the vector 1 to 1. So it's a very good way to describe the solution. So I don't only have it, but I have a geometrical intuition for it. So every solution, it means every number x1, x2, x3, every ordered triple of numbers, they are on this line. Because the vector x1, x2, x3 is a scalar times that. So if this is the point x1, x2, x3, means this vector from here to here is a scalar times that. So the solution are everything on this line that go through the origin in this direction of 1 to 1. And that's the geometry of the picture. So it doesn't only let me write the solution in a good way, it also helps us actually to understand it. Now, another way you can also see it, that it's actually the span of the vector 1 to 1. Every solution is scalar multiple of this. It means it's actually the solution are the span of this vector, but they are all linear combination of that vector. Now, example number 2 will be, what if my system is still homogeneous for now? What if my system have 2 free variables? How can I write it in a vector form? All right, so I'm gonna take another example, how to write the system in vector form if we have 2 solutions. So this is our problem. Solve the following system and write the solution in parametric vector form. And that's the way we'll be asking the question so on. If I ask to solve the system, I'm gonna write it this way. All right, we're gonna solve the system. and we always solve in the same way. So I'm going to start solution. I take my augmented as usual. And that's again a homogeneous system. So we know that we have at least one solution. Okay. So we're going to solve it. So 1, 3, 5, 4, 0. Minus 1 plus 1 is 0. That's give me a minus 1. And that's going to give me a minus 3. Minus 4 plus 1, it's a 3 and a 0. I can stop at this stage if I want, but then I will have to do back substitution. Or I can go one step further because it's a simple scenario. So now I have my leading. I can go one step further and go to the reduced echelon form, which will save me the back substitution. So let's do that. Multiply this by 3. So those will not touch at all. 3 minus 3, that's a 0. Multiply this by 3, it's going to give me minus 9 plus 5, minus 4. Multiply that by 3, which is going to give me a 9. 9 plus 4 is 0. And then I will have a 0. And I'm going to cheat here, minus 3 and a 0. All right? 3 minus 3, minus 9 plus 5. Multiply by 3, 3 times 3, 9, plus 4, 13. All right? So that's my reduced echelon form. And now we're going to solve exactly like we did before. First, basic R, x1, x2. Free R, x3, x4. And the system that correspond to the augmented is x1, zero, and x2 equal to 0. Okay, so let's see what's going to be my general solution. That's not the parametric, the general solution. You write it x1, no more confusion because the solution consists of 4 numbers. That's the way we want it. This is my free variable. This is my free. Now, because I went to the reduced echelon form, I can pick up x2 from here. Remember, everything has to be in terms of the free. And this will give me 4x3 minus 13x4. So that's the piece you know so far. Now, what is the new piece? Now, that's the new piece. My free variable, instead of keeping them called x3, x4, what I'm going to do is, so that's the parametric part, so we're going to set x3, we're going to give it a letter name, S. Okay? And x4, you can give it any letter name, you can call it a T. And now I'm going to rewrite everything in terms of S and T. It's less confusing than keeping x3, x4. So we write in terms of S and T, that's what we call the parametric form, and then 13T, and then x2, you can use any symbols under the sun you want, I don't care, plus 3T, and x3 is S, x4 is T. ST, take any value. Okay, so now as I change S and T, I will change the solution. So that's where the infinitely many solution comes in. So that's the general solution. Now we're going to write it in vector form. Now in vector form. So let's write it in vector form. And let's see how we do it when we have 2 variables. All right. So I will keep this in front of us because we are here. Now, the way we think is, suppose X is a solution. X have 4 components because my system has system of 4 unknowns. And this is equal to, okay, first I copy verbatim, and then I'm going to decompose. S and T. Okay, now let us decompose the solution. How do we decompose it? Okay. All right. The way we're going to rewrite this is as follows. We're going to write it like that. S, the parameter S, I introduce times a vector, plus the parameter T, I introduce times a vector. That's how we are going to decompose it. So I'm going to have the parameter S and T. And then I honestly fill in the gap, what's really left. So now, I'm decomposing this quantity into two vectors. So it's going to be written as for S minus 13. What you write here should be verbatim the same. Minus 3 plus 3. Now S is 1, it's a 0, that's a 0, that's a 1. So that's how we are going to decompose if we have two free variables. And as I said, what you have here is what you have here. So if I combine for S minus 13t, that's the first entry, minus 3S plus 3t, that's the second entry, S plus 0, that's in S, 0 plus t, that's a t. So that's what we call, so that's the parametric vector representation. That's what we call the parametric vector representation of the solution set. Sorry, parametric vector representation.
Could we also say parametric vector solution?
Parametric vector representation of the solution. Okay, that's how the book uses it. So it's like, because it's the way you're representing the solution, because this is also the solution of the system. Okay, but this is a way of representing it, that we call parametric vector representation. Okay, that's how we use that. Now, but this is actually, it's really nice to represent the solution, because now I know that every solution is basically a scalar times this vector plus a scalar times that vector. So one way, if you want to use the language we're developing, you can say that the solution is actually, you can think of it as the span of two vectors. The span of two vectors. So it's the span of that vector. That's one way to think about it. And this vector. Now we know that 0, 0 is a solution obtained for S equal to 0. And we can think of the solution, we can say that the solution in this particular case is the span of those two vectors. It means every possible linear combination of the two vectors. So
when we think about it that way, we don't have to put S or T because it can be any number, correct?
Exactly. In this part, when it is homogeneous, because when it's not homogeneous, which I'm going to do right now, this kind of doesn't work exactly this nicely, okay? But in this case, yes, the solution is the span, because that's what it is. Every possible linear combination of those two vectors. That's really what it is in this particular scenario. Okay, so it really helps us understand the solution actually much better than before. Instead of being like the stuff here, now we actually can see it, right? The second example is, what if the system doesn't have, not homogeneous? So what will be the situation? So the example now I'm going to take is non-homogeneous equation, right? So it's not an easy, today's section is not hard at all. We'll leave the hard for next time. So non-homogeneous system. Okay, non-homogeneous system is a system of the form Ax equal to B, but the B is not 0, nothing. Okay, so in the homogeneous, this has to be 0. Now, this doesn't have to be 0. So in the homogeneous, in the non-homogeneous, we have an issue. The system does not have to be necessarily consistent. However, in the homogeneous, it's always consistent. So sometimes not consistent, and sometimes, of course, it has to be consistent. Otherwise, it makes no sense what we're doing. So the question is again here, solve and write the solution in parametric vector form. To solve, write solution in parametric vector form. So I'm going to do verbatim what I did before. We're going to solve, and then we are going to write it. So solve it. -1, 2, 1, -4, 2, 3, 2, -7, and 1. Okay, so this is, we're gonna solve, try to do it very quickly. And then I will have 1, 1, -3, -1. And then -2 plus 2 is a 0. That's a -1, that's a 6, that's a 2. And then this has to be multiplied by -2. So give me minus, that's a 2, 2 plus 2, it's a 4. If I do any stupid mistake, you guys make sure to correct me. -3 plus 3 is a 0. -3 plus 2 is a -1. -3, sorry. 3 times -3, -9. No, -3, I'm multiplying by -3. 9 minus 7 is give me a 2. I'm multiplying by -3, so it's gonna give me a 4.
Wait, that was 9 plus 7. It's not 9 minus.
-7.
Is it -7? Oh, you're right. Okay, yeah.
Yes, yeah. I do mistakes. So you guys, as I said, I'm fine if you correct me. Now, leading. Everything below the leading has to be 0. Everything below the leading has to be 0. So, and that's not very hard. Actually, you guys can see already that those are exactly the same. So 1, 1, -3, -1, 0, -1, 2, 4, 0, equals 0, 0, and a 0. The last step is I want to go to the reduced echelon form because I think it's easy. You don't have to. I do it when I look at it. I said, you know, one more step and I will be in a good shape. 0, 0, 0, 0. And then I will have 1. This is 0. I have -1. I have a 3 in here. And I'm going to flip those signs, which give me that. So now I'm ready. We are ready to solve. So this is basic. This is basic. This is my free variable. So let's do that. Let's see what we're getting. So we're gonna get the following. x1, x2, those are the basic. And x3 is free. So we write the system and then the general solution, then we introduce parameters. So the system is x1 minus x3 equal to 3. And x2 minus 2x3 equal to -4. So let's write the first general solution, x1, x2, and x3. All right. x3 is -4, sorry, my apologies. x3 is my free variable. x2 is -4 plus 2x3. x1 is 3 plus x3. Okay, now I'm going to choose parameter and then in vector form. So parameter, I only have one free variable. So now we introduce the idea of a parameter. So we're going to set x3 to be equal to t and express everything in terms of t. But that will be definitely easier for us to deal with it. So x1, x2, x3. I call this is a t. x2 become -4 plus 2t. x1 is 3 plus t. Okay. Now we're going to take this and learn how to write it in vector form. And let's write in vector form. So in vector form, it means now I'm looking at, that's my solution. It consists of 3 numbers, x1, x2, and x3. And I can write those numbers using matrix notation. And the solution, every solution, that's what it is. It's x3 can take any value. x2, once I know what x3 is, x2 will have to take this value, and x1 will have to be 3 plus 2. Now the question is how to write this using vector form. What's the vector form representation of that? Now I have one parameter t, but obviously I cannot factor it out because I have those constant term here, 3 minus 4, 0. So how are we gonna rewrite this in vector form? And that's how we do that. We'll do it the following way. We're gonna write it as, so we're gonna factor out the t, but I cannot factor it out across. We can factor out, we're gonna write it as t times 1, but then I have my constant term. 2t, then I have my constant term, and it's a 1, and my constant term is 0. Okay, so the way we're going to write it this time, we cannot write it as a scalar multiple of 1 to 1, which is absolutely wrong because I don't have a t in here, but I'm going to break it into two pieces. I'm going to write it a scalar multiple of this vector plus a fixed vector, 3 minus 4, 0. And this will be the parametric vector representation for this situation. Okay, so it's a scalar multiple plus this vector. Now, geometrically, so that's how we, now let us a little bit understand this geometrically. Okay. It's not a span of a vector. Span of vector is all linear combination. But here I'm not taking linear combination of those two. I'm scaling this vector that I'm adding a constant vector to it. So how are we going to visualize this a little bit geometrically? Can anybody think a little bit about it? So if I take any point, x1, x2, x3, any point, such that if I take the vector which start at the origin, which tip at this, it's equal to t times that plus this. So where is my vector? Or where is the tip of it? Let's do a bit of geometry. All right. 1 to 1. I'm going to draw the vector 1 to 1. So this is 1 to 1. Okay. And I'm going to draw the vector 3 minus 4, 0. So let me see, the vector 3 minus 4, 0 is here. So far I'm just drawing those two. I'm trying this vector, I'm drawing this one. Okay, and now I'm going to draw solutions. What is the solution? If t equal to 0, then 3 minus 4, 0 represent a solution. It means if I put in 3 minus 4 and 0, I'm getting minus 1. 3, 6 minus 4, it's a 2, I'm getting a 2. 3, 12 minus 8. 3 times 3, 9, 9 minus 8 is going to give me 1. So if t equal to 0, I getting one solution. So which is this one here? That's a solution. But how can I get another solution? Okay, every other solution is obtained the following way. You scale the vector 1 to 1, and then you add 3 minus 4, 0. So if I scale this by 1, then I add that, I'm going to get this vector. Scale, and then add. So this is another vector solution. Another solution, yes, scaling the first vector. I scale 1 to 1, then I'm going to add 3 minus 4. I can say it in the negative. So I'm going this way. Negative, and then I'm going to add 314. So if I keep doing this, all those vectors that satisfy this condition, their tip is going to be right there. That's what's going to be. Okay, so it's basically taking the vector 1 to 1 and translating it by the vector 3 minus 4, 0. So that's a non-homogeneous system. It means 0, 0 is not a solution. What's a solution is 3 minus 4, that's a solution. Sometimes we call this a particular solution because it's obtained by setting t equal to 0. So sometimes called a particular solution. And every solution is a scalar of 1 to 1 plus this particular solution. So one way to describe the solution geometrically, the solution are all the points x1, x2, x3, all those points, such that the vector x1, x2, x3, I mean by that the vectors that start at the origin with tip is on the line. Now we're describing the line. Is on the line that passes through the point. It's not the origin anymore. I'm going to describe this line. Passes through the point 3 minus 4, 0. So that's a point on the line. That's a point on the line. And in the direction of the vector 1 to 1. Okay, so the solution is, every solution is going to be on the following line. That's the particular point. That's the point, and that's the direction. So that go through this point in the direction of the vector 1 to 1. So this way of writing is again so interesting because when I wrote it without vector notation, it was not clear what is the solution. Now we can actually see it. And it means that basically those three planes, they intersect. Where do they intersect? They intersect along the line that go through this point, and it's parallel to that. In the direction means it's parallel to this vector. Now what we're going to do is we're going to compare two things, two systems. Okay, so that's the vector representation. It's not actually, very hard. You just make sure you do the homework. Now we're going to compare two problems, and you're going to see what's the relationship between the two problems. So I'm going to take the following two problems that I've already worked them out, but I'm going to do them again. So we're going to compare the following. I'm going to compare the following. I'm going to compare the solution. Suppose A is fixed. That's a fixed matrix. I'm not going to change it. The solution of the homogeneous system AX equal to 0, the solution of the homogeneous system, and the solution of AX equal to B. It means if I have two systems, they have the same coefficient matrix, but the constant terms is different. This is the homogeneous and it's non-homogeneous. What's really the relationship between the solution? Okay, so let me take a system that I worked on. We don't really have to do much. Suppose I take the following system that I would like to compare. The one I did today. The one I did at the beginning was x1 plus x2 minus 3x3 equal to 0. And 2x1 plus x2 minus 4x3 equal to 0. And 3x1 plus 2x2 minus 7x3 equal to 1. That's the homogeneous. I'm going to compare it to the following. The one I did a minute ago. The same. This piece to the left is the same, but I'm changing that. equal to 1. Now, what's the relationship between their solution? What's the relationship? Be very careful. This is the same. But this is homogeneous and this is not. What's the relationship between both of them? All right. Let's remember how we solved them. And let's see immediately what's really going on. How did we solve both of them? It's the same approach, basically.
Solve the system.
We solved the system. What's changed between solving that and solving that? What's changed? The last term is changing when we are doing the echelon form. Okay, so let me make myself very clear. Suppose I'm solving the following system, this one. It's 1, 2, 3, 1, 1, 2, minus 3, minus 4, minus 7. That's a 0, 0, 0. Okay, now when I did that, we got 1, 1 minus 3 is 0, 0, 1 minus 2, 0, 0, 1 minus 2, 0. And then we kept going, and I will keep going. But I want to immediately contrast it with what if it is not homogeneous? Will the row operation change? Will the row operation change? Minus 1, 2, 1, minus 4, 2, 3, 2, minus 7, 1. Will the row operation from here to here will be the same from here to here? Yes or no?
Yes.
Yes. The only thing would change will be what? What happened?
The last column.
That's what really changed. And that's really what's going to trigger the relationship between them. So this is going to be 1. That's going to be a 0. This is going to be 1. And this is minus 2. Again, we got, no, sorry, it was okay, 1 minus 2. And then this will give me minus 4. And this is going to give me a minus 4 right there. All right. The operations are the same. The operations are the same. So if I go one more step here and one more step here to the reduced echelon form, what's going to be the effect? The reduced echelon form here, the reduced echelon form here will be the same. It's this term which change. So if the same thing happened, 0, 0, 0, 0, 0, 1, minus 2, 0, 1, 0, minus 1, 0. Here I get the same. That's the last term, and that's sometimes 0. 0, 1, minus 2, and this gave me a minus 4, and that's give me 1, 0, minus 1, and 3. So the same row operation. How will this affect the solution of the system, and what's the relationship between them? For the homogeneous one, what was my solution? It was t times, when I solved, x1 is x3, x2 to x3, and this is 1. When I solve the non-homogeneous, what was the situation? The first part remained 1 to 1 because it's coming from here. But I have to add the constant factor, 3 minus 4, 0. So if I keep the same coefficient, the relationship between ax equal to bx equal 0 in terms of solution, so the solution of ax equal to b is, you can think about it as like the solution of ax equal to 0, but you're translating it by a vector plus a vector. You're basically translating the solution. Geometrically, this is what? Geometrically, it's the following. Okay, that's the geometry. Actually, I draw it. The geometry is, for ax equal to 0, every solution is a scalar multiple of 1 to 1. So if this is my 1 to 1, That's the solution. That's my solution. Now, the solution of the non-homogeneous system is basically you translating this by 3 minus 4, 0. And the non-homogeneous system will have this as solution. So it's the homogeneous, you shift it. And right here is the solution of AX equal to B. So that's the relationship between, if we have the same coefficient matrix, and that's the relationship between actually the two solutions. So if this one has infinitely many, this one will have infinitely many, granting there is at least one of them. And that's the interplay between homogeneous versus non-homogeneous, as long as A is actually have exactly the same coefficient matrix. That's the effect on it, right? So that's the idea of solving a system in parametric vector form. So it gives us the solution in such a way we can absolutely understand it very well. Right. Now, the remark that I gave here, I will be using it in the following way. Suppose we ask the following type of questions. So now we're done with parametric representation. I'm going to ask you the following questions. One question we'll be interested in is the following. Suppose I have a coefficient matrix A. So A is fixed. And the question would be, can we find a solution for all vector B? So if I fix A and I change B, can we always find a solution? So let me make up a problem to make this clear. So question is, let A be the following matrix. Let us say 1, 2, 2. And minus 1, 0, 2. And 2, 4, 2. And let B be any vector, B1, B2, B3. Okay, sometimes we ask ourselves, do we have solution regardless what we plop in here? So the question is, does the system AX equal to B? Does the system AX equal to B has a solution for all B? Means regardless what you put here, can you find a solution? I don't know. There's one way to know, is to solve. So what does it mean to solve AX equal to B? It means we have to solve the system with the following augmented matrix. B1, minus 1, 0, 2, B2, 2, 4, 2, B3. And ask ourselves, can we always find a solution, or there are some values of B that will stop us? One way to answer all those questions is really to have to go to the echelon form. You have no other way to know what's really going on in here. So we go there. So it's a 1, it's a 2, it's a 2, and it's a B1. And then it's a 0, it's a 2, it's a 4. I'm adding, I am adding. So don't let symbol get in the way. Now, I want to make this into a 0. Minus 2 plus 2, it's a 0. Minus 2, minus 4 plus 4, it's a 0. And I will have minus 2, it means minus 4 plus 2. Minus 4 plus 2, that's going to give me a minus 2. So it's kind of nice. And finally, what should I have in here? Here I should have, I multiplied by minus 2B1 plus B3. Okay, so it's relatively simple. And now my question to you is, does AX equal to B has a solution for all B? It means, can I always find a solution for this system, regardless of what I put to 0 for B1, B2, and B3? Yes or not? Okay, Chris said yes. Chris is correct. Chris has to give me an explanation.
Because no matter what we put into B1, B2, and B3, because we have because we have that -2 in the third column there, it will always be a unique solution.
Right. So he said, I don't care about unique actually. What I really care about is if there one. If there one. Not unique in this particular scenario. So answer is yes, because what stop a system to have a solution? What stop the system is a scenario like that. That's what stop a system. Is there a way we can have this scenario, and actually since I have 3, can we have this scenario in this particular problem? And the answer is absolutely no, because so there is the solution exists, yes, because there is no row of the form of the following form: 0, 0, 0, non-zero term. Okay, because every row, and that's important, because each row of the coefficient matrix, each row of the coefficient matrix has a leading. So what's happening here, if I focus on this piece here, each row has a leading. So this means that I cannot have a leading in the last column. Each row has a leading of the coefficient matrix. This piece, we have a leading everywhere. This scenario cannot occur. So each row of the coefficient matrix has a leading, so no scenario of this form. So the solution, the system is consistent. No scenario of the following form. So we're really trying to study nothing of this form. All right, so does the system has a solution for all B? Immediately, yes, because each row here of this piece, I always have leading. Now, there is no way I can create a situation where there is no solution. Okay? That's how we analyze those kind of situations. Okay, time is up for now. I'd like to make one comment. Some students are finding the time for the quiz not long enough. The basis of my choice of the time was honestly as simple as that. When I was teaching it face-to-face, my quizzes were 20 minutes. I doubled the time. But it seems that some of you are still not having enough time. So next time we have the quiz, actually very soon we have an exam, not a quiz. Next time we have a quiz, I will give you more time so you guys will not have to deal with, I don't want tech to get in the way of you doing your quiz as well. All right?
Okay.
Okay, any questions? But please, what I want from you is to do the homework. There is no way you're gonna learn this material if you don't do it. So please do the homework for Thursday and for Wednesday, and come with questions. All right? Any questions for me?
Yeah, when is that exam?
I think it's next week. On Thursday, I meant on Wednesday, I will talk about it. All right? Any other questions?
Yes, could you please bring back the paper with the definition for what was it?
Homogeneous?
Yes, please.
Yeah, okay. You guys can go, and I will stay with any of you who want to have any questions.
Okay, let me get this down, please.
This one, right?
Yes, could you go a little lower, please? Okay, thanks. Let me get this down here.
No problem. and you know, if you want, you can stay. Or no, better in my office hours, just in case there are other students. Just go on Brightspace, and there is a link to my office hour that are held on Wednesday from whatever, from 3:30 to 4:30. Okay.
Okay.
Are you done?
Yes.
Take your time, not in a hurry. Nina, can you hear me? Nina?
I'm sorry?
Yes, I can hear.
Okay, all right. So meet me at 3:30. It's on Brightspace at the Zoom. Use the link, okay?
Okay.
Does anybody else have any questions?
Two last things. One,
Sure.
could you bring the would you please bring back the paper that compares AX equals 0 to AX equals
Sure,
B?
sure. Okay, I shouldn't have. Give me a minute. I don't know where I put it. It is right there
Okay.
with me.
So I'm with you. Just a second here.
Yeah, this one I did it lengthwise, so I can compare them much easier. Let me
Thank
see
you.
if I push this up a little bit. Wait.
Could you please go a little bit lower, please?
What?
Could you please go a little bit lower? I'm trying to see some writing there.
This one?
Yes.
Okay, do you understand the writing?
Yes. Solution of AX equals 0 plus vector.
Right.
Okay, let me just get this down, please. Solution of AX Okay, I got it. Thank you.
Sure.
Last question. Going back to the quiz, the question about the span.
Yes.
I didn't quite. I didn't quite pick up on something you said there. Did we have to make a graph or no?
No, not necessarily. No. No.
Oh, just describe.
Just figure it out. Is it a line? I mean, that was my question. Is it a line? Is it all of R2? Or is it a plane? That's really what my question was. The student who identified it correctly got the grade. I mean, those who told me for the first one a line, the second R2, the last that got the grade.
Okay.
All right.
Okay,
I draw the picture for you to visualize. Otherwise, it's impossible.
Right. Okay. So just state what
Exactly. Just
what
state.
the span is.
Yeah. I did not ask for any picture whatsoever.
Okay. All right. That's what confused me. Actually,
Sure.
I should have asked. Okay. Thank you very much. I think that's it.
Okay. Great.
Take care.
Anybody else? Anybody else has a question before I end the meeting? Anyone? Okay, if you guys have anything, you can email me and I'll be glad to answer you. Bye-bye for now.